Welcome to the Explainer. So today we are tackling a massive, chaotic, and frankly fascinating challenge going on behind the scenes of modern artificial intelligence. Data doesn't just fall from the sky. To train large language models, scientists actually have to scrape the vast, raw internet. But the internet is a completely wild place full of absolute garbage, weird formatting, and just endless repetition. Today, we're exploring exactly how computer scientists actually tame this incredibly raw data pipeline. Imagine the internet for a second as a massive, fast-moving, incredibly muddy river. If we want to teach an AI, we can't just have it drink the mud, right? We have to pan for gold. An AI model is fundamentally only as good as the data it learns from. If you feed it nonsense, you're going to get nonsense out. It's that simple. But how on earth do we sift through billions of web pages efficiently? Okay, let's dive into this because sometimes the mud in that river is absolutely hilarious. Get this. When researchers were looking at a massive, seemingly filtered dataset called C4, they found one specific string of perfectly grammatical English text that appeared an astonishing 61,000 times. What was it? A completely random text description for a graffiti mask drawing product on Amazon. No way, right? It's perfectly fine English, sure, but you absolutely do not want your massive AI to train on this exact same Amazon product description 61,000 times. That is just a massive waste of computing power. So, to fix this, here is our technical journey today. 1. Taming the raw internet. 2. The art of filtering. 3. Algorithms for quality control. 4. The duplicate data dilemma. 5. Erasing exact copies. And finally, 6. Catching near duplicates. We're really splitting our focus into two main superhero steps today: filtering, which is assessing quality, and deduplication, assessing uniqueness. Let's get started. Part 1. Taming the raw internet. Taking a tiny pile of gold to find more gold. To tame the web, the brilliant high-level primitive is to take a tiny set of known high-quality data. We'll call that your target data, and use it to search through the massive raw web to find more data that looks just like it. You're basically taking a tiny pile of gold to help a computer recognize and extract more gold. Let's break down this fundamental recipe. We can think of this four-step process kind of like a nightclub bouncer. First, you get your target data. That's the VIP list. Second, you train a classifier. So you teach the bouncer what a VIP actually looks like. Third, you score the raw data. The bouncer checks the ID of every single piece of data at the door. And finally, you just keep the high scores, letting only the best data into the club. Part 2. The art of filtering. Setting up the bouncers. Here is the catch, though. When setting up these bouncers, you are running this check across the entire internet, so they have to be exceptionally fast. If your filtering model is too large or too slow, it'll literally cost you as much time and money as actually training the final AI itself. This brings us to the tools of the trade. On one hand, we have n-gram models. These just count local word sequences. They're incredibly fast, but they're a bit crude. Because they only look at the words immediately next to each other, they can actually be fooled by structured gibberish that just happens to have common word pairings. On the other hand, we have FastText. This is a much more efficient linear bouncer. It takes a bag of words approach and maps the vocabulary into a smaller hidden dimension. It doesn't use complex, deep neural layers, which gives it blazing speed while still successfully categorizing whether a document is good or bad. Part 3. Algorithms for quality control, defining what makes data good. So we've set up the bouncer, but how do we define what makes data good in the first place? Finding that initial high-quality target data can be incredibly difficult, so researchers have to get highly creative. Listen to this brilliant modern trick. To get high-quality target data, researchers are now actually using advanced models like GPT-4 to synthetically generate it. They literally give GPT-4 a prompt, like asking it to determine the educational value for a coding student. GPT-4 generates or scores a small batch of pristine target data. Then, the researchers use that small batch to train their ultra-fast, lightweight classifier, like FastText. They're using the heavy, smart model to teach the fast, simple model what to look for. It's a real game changer. Part 4. The duplicate data dilemma. When good data becomes a bad thing. So even if we filter out all the low-quality garbage, we still hit a massive hurdle. Sometimes perfectly good data becomes a bad thing. Take the standard MIT software license. It's high quality, proper English, right? But if your AI reads it 10 million times because it's copy-pasted across the entire web, the AI will over-index on it and ruin its training. So the crucial point is this: we absolutely must deduplicate. But fundamentally, comparing billions of web pages pairwise, page A to page B, then page A to page C, and so on, that takes quadratic time. It is a mathematical impossibility at the scale of the internet. We desperately need clever linear time shortcuts.
Part 5. Erasing exact copies, the clone sweepers.
To sweep away exact clones without comparing every page directly, computer scientists rely on hash functions. A hash function takes a massive document and mathematically crushes it down into a tiny integer, or a really short string. Instead of comparing whole documents word for word, we just compare these tiny integers. But storing millions of hashes still takes a massive amount of memory. Enter an elegant solution, the Bloom filter. This is a highly memory-efficient probabilistic algorithm. It acts like a massively efficient bucket system. The catch? It allows for a tiny fraction of false positives, meaning it might accidentally delete a unique document thinking it's a duplicate, but it will never produce a false negative. If it says an item isn't in the set, it definitely isn't.
And this brilliantly illustrates how it actually works. Imagine a long row of zeros. When a document comes in, you hash it multiple times using different seeds. Each hash gives you a number, and you go flip the zeros at those specific positions to ones. To check if a new document is a duplicate, you hash it. If all its resulting positions are already flipped to ones, you treat it as a duplicate and toss it. Want to make fewer mistakes and drive down false positives? Just increase the number of hash functions, which we call K. It's so simple, but so powerful.
Part 6. Catching near duplicates, the shapeshifters.
Okay, exact copies are handled, but what about the final boss of data curation, the shapeshifters? What happens when a duplicate is just missing a comma, or someone swapped out a single word? An exact hash will completely miss this. It'll just see them as totally different documents. To catch near duplicates, we first need a mathematical anchor for similarity. We use something called Jacquard similarity. It's beautifully simple. You take the words two documents share, their intersection, and divide it by the total unique words across both documents, their union. Now, what's really interesting about this is how sneaky near duplicates can be in the real world. Think about a phrase like best actor in a negative role compared to most impactful character in a negative role. They are practically identical in meaning and structure, just with a few words swapped out. If an AI reads variations of this millions of times, it's not learning anything new at all. We need to catch this. But again, comparing every page to every other page using Jacquard similarity takes way too much time. This is where we bring out the heavy algorithmic artillery, Locality Sensitive Hashing, or LSH. Using a miraculous trick called MinHash, we can actually turn that slow pairwise comparison into a single item hash function. With MinHash, the probability of two documents producing the exact same hash collision is mathematically equal to their Jacquard similarity. It's like magic. More similar items naturally group into the same buckets.
But we don't just want a gradual curve of similarity, right? We want a strict rule. By grouping these hash functions into what we call bands and rows, researchers can bend the probability curve into a sharp cliff. In one major AI paper, they tuned this algorithm to a strict cutoff of 0.99. This incredibly tight threshold means that for every 100 words, literally only one word is allowed to be different for it to be instantly flagged and deleted as a duplicate. It is incredibly efficient running across the whole internet in linear time. We've seen how scientists pan for gold, train fast bouncers, and use brilliant mathematical hashing tricks to sweep away exact clones and shape-shifting duplicates. But it leaves us with a really provocative thought. Today, we use AI to generate data to train filters, but as the raw internet fills up with more and more of this AI-generated synthetic data, it's changing the very nature of noise on the web. So how will our deduplication algorithms have to adapt next? Thank you for joining me on this explainer. Keep learning, and I'll catch you next time.